All right, looking at number 17C here, okay, so we're gonna want our x. X would be what here? What's our x? Because this is something you gotta be able to do with the calculator, right? Because on a quiz, if you come to me and say, hey, I can't see my graph, what's wrong? Well, you can't see your graph, it's your window setting. So probably what I'll say is, well, it's probably your window setting, right? And you've got to know in the problem, and a lot of times I give you some window settings, but you need to be able to do that too. And so I may not give you window settings. So you got to know, what do the things stand for in my problem? So what does that stand for in this problem? What does X stand for in this problem? Remember when Lacey typed it in, she accidentally typed what wrong first? You put a T and then you change it to an X, right? So what's X in this problem? Thank you. Jeez, you guys are the quietest calculus class I've ever had in my life. Thank you. T is time, right? Now, again, X. Now, if you're thinking of parametric equation, we got X and we got Y, which is position, right? Horizontal position, but not what we're doing right now, right? What we're doing right now, X is time, okay? Because we had to, when we typed it in, we typed the equation in, we had T in, okay? All right, so what would be our time in this problem? What would be a range of time here? To 0 would be a good start. Throwing the baseball. How long did it take to get there? 0.4, right? So no more than 1. I wouldn't say no more than 1 second, okay? So 1. And then what's our y here in this graph? But what's the y? What is the y representing? The speed. No, in the parametric graph, x and y were, right, the distance of the ball and the height of the ball. But in this graph we're doing right now, we're graphing s of t, we're graphing speed, right? So the y is a speed. So what's the speed start out at? No, what's the speed start out at when we throw it? 150, and then what happens to it? It actually speeds up just a teeny bit, right? So what do you want to start your y? Say 150, and then what for the max? 152, I mean, it doesn't speed up very much, right? Okay. I mean, it's a tricky one, I get it, but this is the point I was talking about in these problems, because that's what we're moving into. You're going to see today. The homework today has like 5 problems. And it may be the hardest homework we've had all year. Way to brighten up our Friday. But why is that? Because what we're going into is story problems. This might be one of the hardest sections that we do, and it's one of the things that's just because it's kind of like in Algebra 2. You got to set up those story problems. It's setting up the problem is the hard part, right? But the key to setting them up, one of the keys to setting them up is setting your variables and knowing what your variables represent, right? And so this is a great example of this. Okay, so we've got to be thinking about what they represent, and that's how we get it. So now we get a nice graph. Otherwise, you can search for a long time and never find this graph on your screen. Okay, so now it says, how does this represent the physical situation? Well, what's this graph doing? It's increasing. And what did we say was happening in this situation? The ball was speeding up, right? The ball was speeding up because as it was going, no air resistance, gravity's dragging it down, so it's picking up speed, picking up speed, picking up speed. And it would continue to pick up speed if it never hits the ground, right? If it never hit the ground, it would just keep getting faster and faster and faster and faster, and that's what this is. Okay? So it was just a question about interpreting what is happening. Okay? All right, good question. That's what I'm talking about there, right? That kind of question where you look at that and you just, there's a concept behind what's going on and you don't get it. So let's talk about it. Okay? The mechanics of doing those, which is what number 20 was, just plugging into the equation and doing that, right? You've got to come talk about that. If you're having trouble getting things plugged into your calculator, with these equations, let's talk about it. All right. And also in the video, I have a video yesterday where I went through that too. I mean, that's another resource if you don't want to come talk to me about it. All right. And then 19, was it 19 or 18? That was where you just did basically the same problem as we did, but you changed it to 100 feet per second, right? I mean, so that was pretty much the same chance. So a couple different chances to go through those things. All right, anything else? Anything else on the parametric? The circle, we're okay with that. What happened there? You just didn't have the calculator. Okay. All right. Well, I'll tell you what. Let's do this. So, if you have some lingering questions about that, then let's get through what we need to right now, and then we'll have some work time, and then you can certainly ask me about those then. Okay. So that. Don't let that go by. If you've still got some issues with the parametrics. So that's one of the things that will be on our next quiz, the parametrics. And before we have that quiz, because it's still going to be a week and a half away probably, we will talk about, we'll go back and review that a little bit. Okay. All right. So go ahead and get your notes out, I guess, and we're going to see what this next thing we've got going would be. I need to send. So is everybody logged in? All right, I'm going to send you this document. Now, some of you, if you came over from third block, your calculator probably has an AP Calc period 3 folder. And now I'm sending this, and it's probably going to create an AP Calc period 2 folder. Okay, so I just sent you something. Did you get it? Yep. Okay. It's called What is Calculus? And we're not going to need it just quite yet, but you can go ahead and open it if you want to. We're gonna be looking at that here in a little bit. All right. So let's do this. So we're going to be talking about section 4.3, and 4.3 is about something called optimization. 4.3 is called optimization. Now, if you're going to major in business, oftentimes you take an applied calculus class that's required, so it's a little different than a regular calculus class. And one of the differences is, overall, I think it's a little easier than a regular calculus class, but it's focused more on the application side of things. And this is one of the things that they focus on a lot more than a regular calculus does. And it's this idea of optimization. Okay? Optimization means an optimum, okay, means a desirable, right, outcome. And so mathematically what that means is a max or a min, typically. So if I'm a business person and I want to manufacture some product and sell it, then I want to, there are several optimum things. The biggest one, of course, is my profit. I want to maximize my profit. That would be the optimum. Okay? So one of the things that I would want to be able to figure out is, how can I maximize my profit? Now, that might be by minimizing my costs, right? So another optimum situation there might be finding my minimum costs, okay? Now, it also might be maximizing my revenue, right? So that could give me the maximum profit. Revenue is just the money you bring in, right? Cost is what it costs you to make the thing, and then profit is the difference between those two, right? Revenue minus cost, right? How much money do I bring in, subtract off what it costs me to make it, and the rest is my profit, okay? But I could maximize revenue by making more of whatever it is I'm selling. But that might not maximize my profit because to make more, I might have to hire more workers, or I might have to open a new factory or whatever, and then that increases my cost. And if I make too many and I don't sell them, right, then that lowers my revenue while my costs are increasing, and so that might have an effect on profit. So you got all these different things that can play into it. Now we'll keep it relatively simple from that standpoint, but we want to make sure we understand the basics of that. So those are some of the things we're talking about. Now remember the problem we did way at the beginning of the year? You talking about setting up the storage problem. Remember that one we did with the snowmobile, right? Or the guy in the snow, right? Was stranded in the forest and had to get to the service station, and he could walk on the road, or he could go straight up to the road and then over, or he could walk directly, but he had to walk slower, right? That kind of thing. In that case, the optimum situation for him was the minimum time. We wanted to minimize how much time he was walking so he didn't freeze to death, right? So we would want to set up a time function, and that's what that problem was. If you remember, we had to set up a time equation, and then we would want to find the minimum time. Where should he go to get the minimum time? Okay, that would be the optimum. So that's what we're going to be doing. All right? So first, we need to review what it means to find a global max or min, because that's what we're going to be finding. We're going to be finding maximums or minimums of functions. And we've already done that, so this part of it should just be reviewed. Okay? So we'll start with that. So what we're going to do today, and this would be really important to do a good job of taking notes on these ones we're going to do here, because I want to throw out at the beginning all of the different scenarios we've talked about up till now of finding a global max or min. Now this is the calculus part. Now unfortunately the hardest part of these problems is not the calculus part. The hardest part is the algebra part. Getting the proper equation set up. Once we get the equation set up, I think we're typically pretty good at the calculus part. All right? All right, so I've got a function here. And the first thing I want to talk about then in a global max min is where do I look? Where do I look for the possible max and mins? Well, one was the endpoints. Now in this example, it's not my endpoints, is it? Where is my max on this one? Right here. What's happening right there? What's happening right there? Stationary point, which means, what's a stationary point? F prime is 0. F prime of x is 0. That's one place that I look, right? What's my minimum in this example? What's going on there? It's a sharp point. What's going on at a sharp point? F prime is undefined. So we've got to check those places. We've got to check where F prime is undefined. Now those two together make up what are called critical points, right? Those two together are critical points. A stationary point plus where the derivative is undefined, that constitutes critical points. So I've got to check my critical points, where the derivative is 0 or where the derivative is undefined, right? And then you guys also said endpoints. That's right. What happens if I would extend this down to here? Now my minimum is at an endpoint. Or what happens if I extended this up to here? Now my maximum is at an endpoint. So I've got to check my endpoints. Okay? Now, any function that we look at in a closed interval is going to have both a max and a min. We have a theorem for that, which we'll talk about at the end of chapter 4. But that's, we know there's a max and a min if we have a closed interval. And this is where we will look. Now, we talked about making a list of candidates then, right? And the max is the one that has the biggest y value, and the min is the one that has the lowest y value. Because we can compare them. So we have to plug our candidates back into where? The original function, the one we're trying to optimize or max or minimize. we plug our candidates back into the original function f because we want to see what's the lowest y value, what's the highest y value, right? And we do that by comparing them. So in this case, if I plugged in my endpoints, where the derivative is 0, where the derivative is undefined, I plug those into the original, I would see that the left endpoint had the smallest y value, the right endpoint had the biggest y value. Those would be my max and min values. Now, if I wouldn't have extended these, then when I plugged them in to the original, I just saw that the biggest y value was here and the smallest y value was there. And those would have been my max and min, right? Okay. Now, what would happen if we didn't have any endpoints? What if I gave you a function that did this? Now where are the max and min? There aren't any, right? I mean, yeah, infinity, negative infinity, although those aren't numbers, right? So we would say there is no global max and there is no global min, but we don't have a closed interval there, right? So we're not guaranteed that we would have a max and a min. It's not a closed interval. It goes forever, okay? And so in this case, we'd say there is no max and there is no min, all right? Or it's possible that maybe we had a left endpoint but not a right endpoint. Maybe we were going to look at a function from x is greater than or equal to 0. So we'd have an endpoint maybe here, but not one over here. Well, here we'd have a global minimum, but we wouldn't have a global maximum, right? So it's possible to have one and maybe not the other. Now, we got to talk about this idea of list of candidates, though. What happens if you don't have any endpoints? Well, if you don't have any endpoints, you can't really count infinity as an endpoint. Not really. We'll talk about that here in a minute. We can kind of act like it's an endpoint. But if you don't have any endpoints, and maybe you don't have any place where the derivative is 0 or undefined, now you probably have one of those. Like, say, a parabola. You'd have one stationary point in a parabola. And if there were no endpoints, you'd have a minimum but no maximum. But how can you do a list of candidates if you only have one candidate? What's wrong with a list of candidates if there's only one candidate? What's the purpose of a list of candidates? To do what? To find the max value, right? So why is one candidate not going to help you do that? Well, why couldn't it be the max or min? If I have a parabola like this, I have one candidate right there where the derivative is 0. Is that the max or the min? It's the max. It's the max. So if I do a list of candidates, let's say that's at 2. So I do a list of candidates. Remember how we did a list of candidates? And I plug it into the original, and I get 17. Now, is 17 the max or the min? Well, pretend you didn't know what the picture looked like. Is it the max or the min? We don't know. Why not? There's nothing to compare it to. That's why you do a list of candidates. You do a list of candidates so you can compare them to each other. You can see which one's the highest y value and which one's the lowest y value. If you only have one candidate, there's nothing to compare it to. So you don't know. So how do you deal with that situation? Well, here's where you can treat infinity and negative infinity kind of like endpoints. What I'll say is you need to discuss the end behavior. You need to look at the end behavior. Well, guess what that is? You're going to be doing a limit. What you're going to be doing is talking about, hey, what's happening as x goes to infinity and as x goes to negative infinity? What's happening to this function? And in a parabola that's upside down, you'd be able to look at it and say, well, as x gets really big, the function is just going to get smaller and smaller and smaller. So therefore, our one candidate is the maximum, right? That's what you'll look at. So you'll have to, so there'll be times where you can't really do a list of candidates. Now here's the other thing you can do. If you don't like that idea of doing infinity and thinking about the end behavior, you could do a number line. We normally don't do a number line with global max min. But in this case, if you only have one candidate, say you're 2, and it's positive here and negative here, that means the graph is going up. The graph of f is going up, then going down, right? So what you would say, and this is allowed on the AP test, this is the only time you can use a number line for a global max min, is you have to use the word always. You would have to say, since f prime is always positive before 2 and always negative after 2, then there's a global max here, because F would always be increasing before 2 and then always decreasing after 2. And so therefore, there's a maximum, a global maximum there, right? So that's how you can handle a one candidate situation. Otherwise, if you have more than one candidate, you just do a list of candidates and compare. All right, so that is the fundamental idea behind what you need to do with candidates, finding global maximums. But we've done all those things, right? We've talked about all those things and done some problems with all those things, but now we got to come back and put it all together. All right, so let's do this problem right here. So go ahead and do this. This would be a no calculator situation right now. Let's treat this as a no calculator situation, unless you need to type a multiplication or something simple like that. But don't graph it, don't do any of that. Okay? All right, find the global max and min on that closed interval for that function. You work together if you want to, compare, talk to each other, you know, see what, help each other out, right? This isn't a quiz. So. All right, so we start by doing what? Derivative, so that equals 0. Cole, what'd you get for your stationary point? 0 and, 2? Three halves, I believe. Should have been 6/4, not 4/6. Okay? 0 and 3 halves are our stationary points. And so then what do? Plug them back in the original. What else do we plug into the original? The endpoints. Okay? Now, and then, yeah, that's it, right? I mean, and then we see what we get, and the biggest one is the max, and the littlest one is the min. Now, it got a little messy with the fraction and that kind of stuff. All right, so let's see where, okay, so pretty straightforward. This, now again, you know, we're starting with this because this needs to be the easy part of these problems, right? Then we can focus on the hard part, which is setting up the equations. Why this was easy is because I gave you the function, gave you the endpoints, right? It's gonna be about I don't like to necessarily memorize steps, but this is one of those situations, this optimization process, I like to kind of give you a recipe to follow. I think it's kind of helpful. Well, there's about 7 steps in here, right? And it's the first 3 that are hard part. This problem, we're starting on step 4 of the 7 steps, right? And those steps from there on down need to be the easy ones. Do the derivative set equals 0, see where the derivative is undefined, check your endpoints, okay, and that's what we do. So we do the derivative, and this is what I get. So Cole, I'm not sure, maybe derivative wasn't quite right or something.
Yeah, my derivative is 6x squared minus 3x.
3x, okay. So right here, so we're going to factor out a 2x squared. Now, I don't care how much of this work you show below this, but I heard somebody say 4/6 or 2/3 would be, and I see that all the time where people try to solve this in their head and they get 2/3, right? They don't write it out and they end up getting backwards because they divide the wrong thing. So it would be 2x squared equals 0, 3 minus 2x equals 0. So you add the 2x over to there, then you divide by 2, and you get 3 halves. 3 halves, right? So show whatever work you need, but show enough that you get it right. Okay, that's the thing. So those are my 2 stationary points. All right, and so here's my list of candidates right here. Now it's very important that we justify our answer. The only thing I haven't written here that I am going to want you to put in your problems is I should have over here said that f prime is never undefined. And you're going to be doing that a lot in these problems. Because not very often with the functions we do, not very often in the problems we do is the derivative going to be undefined. But then all of a sudden one jumps up where the derivative is undefined and you forget to check for it because you haven't been doing it in most of your problems and you forget about it. So I'm going to make you check that. There are 3, I'm going to talk about the 3 places we have to check. Endpoints, where the derivative is undefined, and where the derivative is 0. Now you could say there's 2 places you got to check, endpoints and critical points. That would encompass all of them. Endpoints and critical points, right? But critical points is made up of 2 parts. where the derivative is 0 and where the derivative is undefined. So we checked where the derivative is 0, and we checked our endpoints in the blue, but what I didn't do in the blue is ever check where's the derivative undefined. Now, when is a derivative undefined? When there's a negative inside of a square root is a big one, although typically if there's a negative inside the square root on the derivative, it was also a negative inside the square root on the original. And if the original is undefined, then it doesn't matter, because when we go to plug it back into the original, it's undefined there. So typically a negative under the square root is not an issue in these problems. Because think about what you do when you do the derivative. You keep the inside alone, right? So if you do the derivative and the inside is negative in a square root, then the chances are the square root was negative inside the square root in the original too. So that's not an issue. What's usually an issue is you get 0 on the bottom. If you get 0 on the bottom. And sometimes you have a function where it's not 0 on the bottom in the original function, but when you do the derivative, it becomes 0 on the bottom. Okay? And so that's something we want to check for. So we need to say that in the problem. We need to say f prime is never undefined, because that shows me, that communicates to me that you check all of the possible places for the max and the min. All right, so I plugged them in there. Now that gets a little tricky without a calculator, but that's what I got, okay, when I plugged in 3 halves, right? 3 halves cubed, 3 cubed is 27, times 2 would be 54, 2 cubed is 8, so there's the 54 over 8 you can see right here. 3 halves to the 4th, 3 to the 4th is 81, 2 to the 4th is 16. You got to be able to do this. There will be some no calculator situations where you run into some fractions like this. Then I just got a common denominator. 1 would be 16 over 16. I'll double those. That'd be 108 over 16, 81 over 16. Then I added 16 and 108, 124, subtracted 81, got 43. So 43 over 16, which is 2 something. So I knew that was my max, 2 something, and I knew my min here was -1. Now, I went ahead and graphed this just to show you. And so sure enough, if we go from -1 is down here. Didn't we get a -1 for that one? Was -1 one of our endpoints? Oh, it was -2. Okay, and at -2, we had, oh, did I? No, it's -1. Oh, I'm sorry, the y value is -2. I got you. So at -1, we get a y value down here at -2. That ends up being my minimum. Okay, here was where the derivative was 0. It was a flat spot, right? One of the places where the derivative was 0, so that didn't end up being a max or min. Then we had the other one, that's the 3 halves, right? And we said it was 2 something, that's the 43 over 16. Okay, that ended up being our max. And then over here at 2, we got, I can't remember, what did we get at 2? What do we have as our output at 2? -1 or 1? Yeah, 1. So it came down there as 1. So there's our global max and our global min. All right? So that's a pretty routine problem. It's one that's got endpoints. It's got a nice, easy derivative. You plug it back in, do your list of candidates. We've got to be able to do that, right? The max min problems don't get any easier than that one. Fractions were a little messy, but other than that, that is one we got to look at. Okay, now do this one. There are no endpoints given. This is -infinity to infinity. So find the global max and global min, if they exist, right, for this function, looking at the whole function from -infinity to infinity. This one, you can use your calculator to solve the derivative. I'll let you use your calculator to solve the derivative on this one, okay? All right. Now, a lot of these, one of my main objectives today is to be able to do, for us to be able to do the basic global max min situation, which is a list of candidates, be able to do your derivatives, where it's zero, where it's undefined, check endpoints, understand you have to plug those back into the original, okay? That is our main focus for this part of it, okay? Now, a lot of the time working over the next several days on this stuff, you'll get to use your calculator. You'll get to use your calculator. Now, very important to understand that your work you show is going to look almost identical whether it's a calculator or a no calculator problem. So let me go back and let me go back to this one. Okay? Let me go back to this one. If this was a calculator situation, everything on here would be here. Let me, maybe in yellow, I'll highlight stuff that probably would not have been here if this was a calculator problem. You may not have done that, right? Because you could have just solved this on your calculator, right? Now, maybe you're more comfortable doing the factoring and that sort of thing. So if you were solving on your calculator, these yellow lines might not be there, right? But this would have to be there with the derivative set equal to zero. This would have to be there, saying that f prime is never undefined. Your stationary points would have to be there. And then this probably wouldn't be there, and this probably wouldn't be there because you would be able to just plug these into your function, you know, on your calculator to be able to get those values. But everything else would have to be on your paper. So you wouldn't be able to just graph it like I did and then say, oh, I traced, and here's the max. That's never acceptable on doing a max min problem, right? Just graph it and trace and see, right? We got to use the calculus to find out. You can sure use a graph to verify and to double check and whatever when you're doing your homework, right? All right, so let's look at this problem. So now I said you could use your calculator. So we do the derivative, we set it equal to zero, we solve it, right? And we get that as our, is that what you got for your stationary point? Okay, and I went ahead and I did that right here. And so I just solved it. I got that, okay? Then I went ahead and used my calculator to plug that back in, right? With the vertical bar, that works good. Remember, I did show you guys how you can plug multiple things into a function, right? With the curly brackets, right? You can plug them all in at once. Like if you have 3, 4 candidates, you can plug them all in at once if you want to do that, or you can plug one in at a time. Okay, so we get this. Okay, now, what's the problem? One candidate. There's nothing to compare it to. We don't know if that's a max or a min. So at this point, you have several different things you can do. All right, I'm going to run out of colors here, but we'll put the different things you could do to finish this in different colors. One thing, somebody got an idea of one thing I can do? What's that? Number line. So one way to do it is to say, all right, I only got one candidate. I really like this, as a matter of fact. I like the number line way of doing it, to be honest with you, because it fits in with what we've done with local max min, so we're used to doing it. So I think that's good. Now, if you do a number line, you've got to label it, because there's a difference between an F prime number line and an F double prime number line. F double prime talks about concavity of the function, so we've got to make sure we know which number line we're doing, okay? 0.367 would go here, so maybe we put like a 0 here, maybe we put a 1 here, and we plug those back into the original. Use your calculator if you want, although those are easy ones to plug in. We put in a 0. Oh, wait, where am I plugging them back into now again? No. List of candidates I plug into the original. What are we doing a number line? What are we plugging in here? Where are we plugging? F prime. That's why we label it, right? We want to see where F prime is positive or negative. We want to see where F prime is positive or negative so we can tell if F is increasing or decreasing. So you got to keep that straight, right? Where you plug it in depends on what information you're trying to get. In a list of candidates, we plug in the original because we want to know what was the Y value so we can compare. On a number line, we're trying to see if the graph's going up or down. Is the graph going up or down? Well, we get that from F prime. So put a 0 into F prime, we get a 1, which is positive. Put a 1 in here, we get 1 minus 3, that'd be negative 2. Negative 2 minus 12 is negative 14. Definitely negative. But now you can't stop there. So you would say something like f prime always positive, keyword there being always, before x equals 0.367, and always negative after, okay? So 0.367 right? X equals 0.367 is a what? It's a max, right? In this case, it really tells us it's a local max. So therefore, and again, usually the question wants to know what is the max. So they want the Y value. So there's our justification then of why that's a max. Okay? So 0.367 is a max. So therefore, and so what about a minimum? There is no minimum. Now, another thing you could do is you could just talk about this is a x to the fourth polynomial. Right? What do we know about x to the fourth polynomials that have a negative leading coefficient? The tails both point down. Right? So you could say, since this is an x to the fourth polynomial, whatever, the tails both point down, there is not going to be a minimum. So any candidate we have is going to be a maximum. Now, it's possible in an x to the fourth you could have several humps, right? You could have several, but then our list of candidates would have worked, right? Although we do have to be careful when there's not endpoints. Let's say I would have had two candidates. Let's say it would have looked like this. I have two different places where the derivative is 0, right? Well, you can't look at one and say it's a max and the other say it's a min, right? I mean, we talked about comparing. You say, oh, I got two candidates. I'll just compare them. One's a max, one's a min. That only works if you have endpoints. If you don't have endpoints, you got to think about what's happening, right? And if you did a number line, you wouldn't do a number line if you had two candidates, probably, okay? But if you did a number line, you'd see it's going up, down, and then you'd have to say, oh, wait a minute, what's going on? So in that case, this would be a good way to do it. If you had two candidates but no endpoints, you'd have to say, hey, what's happening at the ends? There's no minimums. Then you would take, our two examples are maxes. Our two candidates are maxes. The biggest one is the max then. But the other one would not be a min. See, so you've got to take that into account. All right? The other thing you could do is you could just do it as, let me do that in the yellow, you could talk about infinity as if they were endpoints. You could say, okay, as x goes to infinity, let's just look at this. As x gets really big, what's going to happen here? Well, this will be big, but this will be way bigger. And this will be way bigger. Matter of fact, this will dominate. And what's it going to do? Well, as this gets way big and you times it by -3, what are you going to get? This is going to go towards negative infinity. And what if you put a negative infinity in? Well, again, these aren't going to matter. And you put a negative infinity into the fourth power, well, that's just going to make it positive infinity. And then times a -3, again, that's going to go towards negative infinity. So you could discuss that as if they were endpoints. So when I say discuss the end behavior, that's what I'm talking about. So you could say, oh, out at the edges, this is going to go negative infinity. So there's no minimum. Therefore, that's a maximum. So you could do that as well. So you could have the red as your justification. You could have the yellow as your justification. You could, well, you'd have to have more with the blue here, but you could say, hey, it's an x to the fourth polynomial with a negative leading coefficient, so it goes down, no minimum. Our candidate is a maximum. Okay? Somehow you have to justify that min or max. All right. So, let's do a real type of problem here where I don't just give you the function. But first, let's write down our recipe for doing these problems. All right. So, we have an optimization problem. Now, we identify something as an optimization problem whenever they're asking us for a maximum or a minimum, some sort of optimum situation. What's the biggest profit we can get? What's the minimum time it'll take the guy to get out of the snow and to the gas station, right? Anytime you hear a problem like that, you're looking for a maximum or a minimum. You're doing an optimization problem. So the first thing you have to do is identify what it is you're trying to maximize. So if I'm doing a maximum profit, I got to identify that. I got to say, okay, I'm looking for profit. If I'm trying to find how fast the guy can get to the gas station, how fast would mean the minimum time. So I need a time equation. So we need to identify what it is we're trying to maximize or minimize. That is so key. If you don't do that, you don't know where to go. It's the biggest problem people have in setting these up is they don't know where to start. So then we need to write and label an equation of that quantity. So I need, if I'm trying to find the max profit, I need to find a profit equation. I need P equals something. That's another thing people have trouble with, is they don't know how to label their equation. Just call it P if it's profit. If I'm trying to find a time equation, I'm going to do T equals. Right? If I'm trying to minimize my cost, I'm going to start with C equals. All right? If I want to maximize my revenue, I'm going to start with R equals. It's going to be my function. Now, that's called the objective function or the primary equation, right? The book sometimes, some books call it the objective function. Some call it the primary. It's your objective is to find the profit, okay? It's the main equation, like the primary equation. All right? So if I was looking for profit, I might start out my equation being profit equals revenue minus cost. I might just write that out. Okay? Now after I do that, I've got to get that equation in terms of a single variable. So if I write down profit equals revenue minus cost, I don't have any, I got too many variables. I got revenue, I got cost, if I'm trying to find distance or the time that it takes the snowmobiler to get there, well, time would be distance divided by rate. Well, that's two variables. Distance divided by rate, that's two variables. So I need some other information to help me get that in terms of just one variable. So I need to get the equation in terms of a single variable using some other information. And that other information we call our constraints or our secondary equation. Okay? Now, how hard or easy these problems are is determined by how hard or easy these first three steps are. Right? How easy can you get to the function you're trying to maximize? Because once we get the function in one variable that we're trying to maximize, then it's just like the problems we just did. Right? Once we have that function that we want the maximum in for, then the rest of these steps you better know by heart at this point. Once we have that function, we're going to find the critical points of that equation. Right? We're going to do the derivative, set it equal to 0, and we're going to check to see if the derivative's ever undefined. Those are the critical points. Okay? And then we're going to check endpoints. And I wrote down, identify the endpoints or the end behavior. Now here's another thing that sometimes gets tricky. Sometimes they don't just tell you the endpoints in the problem. You have to figure it out. Okay? Like if X is the number of units we're going to produce, maybe we're going to make iPads. How many iPads? Well, what's the minimum iPad? Well, it might be 0. Right? A lot of times 0 is an endpoint in a real life situation. What's the maximum iPad? Well, it might have to do with how many workers we have, and those kind of things. And so there's probably some information in the problem where you have to figure out what your maximum is. They don't just tell you what. I don't want to say maximum. Your endpoints, right? Your endpoints. All right. So we have to identify the endpoints or think about the end behavior if they don't give you any endpoints. All right. Then we just use our list of candidates, or a number line, or some justification to identify that it's a max or min. That was those three different things we talked about in the last problem. They said you can use a number line, you can talk about the end behavior, you can, do a list of candidates. Some justification that this is the max. And then since these are going to be kind of real life type problems, the last step is to answer the question using appropriate units. So if they want to know what the max profit is, then you would give a number with a dollar sign on it. If they want to know how many iPads should we make to get the maximum profit, then you want to say, well, we should make 1,500 iPads or whatever. So you have to answer the question that they ask. Okay? So that's the process. That's the process for doing it. All right, so now open up that document on your calculator that I gave you earlier in the day. The what is calculus document. And we're going to scroll clear to the end of it. To 2.3, page 2.3. Now yours may, one of the reasons I didn't hand this out at the beginning of the year, I used to give this to people at the beginning. I don't think I did. Did anybody have this already? Okay. I used to hand this out, we kind of talk about some things, but it lags so bad. And so I just, when you get onto here, and you try to drag, mine works better because I'm on my computer, but we can drag this thing right here, okay? And here's what this problem is. This is a classic optimization problem. Let's say we took a piece of paper, okay, and we were going to cut equivalent squares out of each corner, okay? That's the white part here. And then we're going to fold up the orange part to make a box, an open-topped box. How big of squares should we cut out of the corner to make the box hold the most? That's the problem. Now, there's a nice little visualization of the problem right here. So this point here is a graph of the volume of the box. Here you get to see the box created. This graph is the volume. And so as I drag this, we can see what the volume does. So obviously the volume of the box is getting bigger and bigger and bigger, but at some point then the box starts holding less and less. Somewhere in there is a maximum volume. And that's what we want to do. Because if I'm making a box for profit, I want to use the least materials possible, right? And I want to make something, it would maximize my profit if it would hold the most. So I'd be interested in what would, for this amount of material, what would give me the most volume. So I'm looking for that point right there, that maximum. Okay? All right, so the question for us, so that just allows us to kind of visualize the situation. So for us, let's attack this problem. So that's what we've got. We're going to start with a regular 8.5 by 11 piece of paper. We've got an 8, so the problem would be worded something like this. We've got an 8.5 by 11 inch piece of paper. You understand the scenario, so it would be written out what's going to happen, right? But now we've already seen it, so we kind of understand. How or what size of squares should we cut out of the corners to make the maximum volume box? Now we'll do this together. So where should we start? Okay, very good. Good job. That's a great idea. Identify the quantity. So what is a quantity we want to optimize? Volume. So I should start by not using the green color. So we should start with V equals, right? Absolute. V equals. This is this is like our f, right? This is our f. This is our function we're going to try to maximize. Now, it's a box. So what is the volume of a box? Length times width times height. Now, unfortunately, that's 3 variables. We don't want to do it with 3 variables, right? We have to do the derivative here in a little bit. And we want to do the derivative with respect to something, some variable. We only want one variable. So what should we do next? Well, what was step 2? Well, that was step 2, right? Write the primary equation. Write an equation for that thing. Well, we just did. Step 3, get it down to one variable, right? Use some other information. Let's get it down to one variable. So what should I do next? No, because we're not there yet. We haven't done step 3. We haven't got this down to one variable yet. So what should I do here? He's pretty good. He just rolling away. He's a good reader. What should we do next? I would, yes, but what I would draw a picture, right? Draw a picture. Often in these problems, there's going to be some picture, right? And matter of fact, that's what I was, when I first said, what should we do first? I was looking for somebody to say, draw a picture. But actually, Doug was a better idea. I didn't say draw a picture, did I? Maybe we should do that. Step 0. Draw a picture, okay? It's not a bad thing to put in there, right? It's not a bad thing to put in there. Draw a picture. So here we go. So we've got a sheet of paper, 8.5 by 11, okay? So this would be 8.5. This would be 11. We're going to cut squares, and they're going to be equivalent squares out of each corner. Okay? So, matter of fact, hint, hint, if I was going to put in my notes draw a picture, I would probably say draw and label a picture, right? So what other labeling do I need in this picture? Length, what's my length going to be? That's going to be this right here, isn't it? And width is going to be that right here, right? Isn't that going to be the length and width of my box? Now where's the height of the box? Isn't that the side of one of the squares? Isn't that what my squares are? My squares are actually going to be h by h, right? They're going to be whatever size square I cut out when I fold it up. That is the height of my box. Okay? So, let's rewrite our equation. So what would be my length here? Won't the length be 11 minus 2h? Right? The length will be this distance right here. Right? Well, that's 11. Take off an h there and take off an h there. So the length is going to be 11 minus 2h. What's the width going to be? Right? That'll be this right here. That's going to be 8.5. Take away 2h. And then what's the height going to be? H. Now, I would say, now since we get to use our calculator, I don't think there's any need to multiply this out or anything. I think we could go right to the calculator and do the derivative, right? You know, when we were doing the gateway test, I said there's going to come a time here when we get to some problems where we want to be able to do derivative formulas. We have no calculator stuff. We got to be able to do derivative formulas, but there's going to come a time where that's just one step in the process, and we'll get to use our calculator for some of these, and this is where we're at right now. So let's assume there's a calculator problem. So you can go ahead and just type that in. Now, you can change it to x if you want, okay, when you do it. But we're going to do the derivative with respect to h, right? We're doing dv dh here. dv dh, derivative of v with respect to h. And to be honest, I don't even care if you write the derivative on your paper. You need to write the equation you're solving. So you would need to put, I'm going to do v prime equals 0 here. Okay, but I don't care that you type it, you copy it onto your paper. And I don't think it's a bad idea. I think it's probably better safe than sorry. Okay. But so we do the derivative. It gives us, now let's solve it, right? Let's do a solve. Let's set it equal to 0. But I certainly have to have v prime equals 0 there. I have to say that I'm setting that equal. And why I'm thinking about it is v prime ever undefined here? Is the derivative ever undefined? Look at the derivative equation on your calculator. Is there any place that it's going to be undefined, which is typically a 0 on the bottom? No, it's just a polynomial, isn't it? Polynomials are never undefined. Sine is never undefined. E to the x is never undefined, right? I mean, so most functions are not. So it's usually if you have a 0 on the bottom, that's what you really have to look for. So let's write that down. V prime never undefined. We don't want to forget that because we got to check. Doug was good to us. He already told us what that next step was, right? Check the critical points. Where's the derivative 0? Where's it undefined? Okay, where's the derivative 0? 1.585. And there's another one. 4.915. Okay? Is that right? You guys agreeing with that? Okay? So we got a couple of candidates here. Now what else? What's next? Doug? Which we did. Derivative 0, derivative undefined. Identify endpoints. Now this is tricky because we haven't had to do this before. In the past, we were just given the endpoints like in problem number 1 here. They just told us what the endpoints were. Now the endpoints are x values. This is the key thing about endpoints here. If you want to jot this down in your recipe of steps, when we say identify endpoints, the endpoints are the inputs, right? It's the smallest and biggest x. In this case, what's our input? What's our input in this problem? H. So it's the smallest and biggest h would be our endpoints. We probably should have done this more towards the beginning, to be honest with you. I mean, it actually doesn't matter when we do it, but what's the smallest h I could have? 0. I always get people, and I'm sure it'll happen this year, come to me and ask, I don't get the endpoints. I don't get the inputs. How do I find the inputs? Well, the key thought is they are the inputs, the x, or whatever variable you have. In this case, we have h. So you have to think to yourself, the endpoints are the smallest x and the biggest x that I can have. The smallest x and the biggest x. Well, the smallest h I could have would be no height at all. And what's the biggest h I could have? How much? Wouldn't it be 4.25? Right? Because if I have an h of 4.25, that would take me to here where I would have nothing left. Right? If I cut out a 4.25 by 4.25, I would just have this thin strip and I have nothing to fold up. Right? In other words, this part right here would be 0, the 8.5 minus 2h. So 4.25 is the biggest h I can have. Okay? Now sometimes you don't have a biggest. Right? What's the most iPads I can make? Maybe they don't give you enough information where you have any constraints. You can make an infinite number. Okay, or whatever. Oh no, there we go with that again. So what's that tell you about this one stationary point then, right? We can throw that out, right? 4.915, because that's not going to work. We could try it. It'd give us a negative volume, so we would know that's no good, right? So now now this is a nice one. This is a good list of candidates problem because I've got some candidates that I can use to compare, and I've got endpoints. So I need v of 0. Don't put f. Don't put f. I know you're used to using f in these global max files, but your function isn't called f. Your function is called v. Okay, now if you want to call your functions f all the time, that's fine, but I think that's silly. When have them mean something in these problems, have them, be similar to the units. So v of 0, v of 4.25, and v of 1.584. Now be careful when you use a rounded value. You probably ought to, use more decimals than that. Okay, we're going to run out of time here, but you plug those in. and you see what you get. Now, when you plug in a 0, of course, you're going to get a 0. When you plug a 4.25 in, you're going to get a 0. That does actually happen often in these problems. We're looking for a max, and the min is 0. You know, the two extremes, the endpoint situations often are zeros. Okay, but it does give us a good comparison. And then, so whatever you get here, that is your max. So then you would answer the question. If the question was what size of squares should we do, then you might say 1.584 inches should be the length of each square. But you'd want to put your max over there, verify, you know, your list of candidates is your justification. All right, your homework is the 4.3. I think it says 4.3 day 1. 4.3 day 1. Okay? Yeah, it's right after where it says quiz 4.1, 4.2. So 4.3 day 1, there's 5 problems. Yeah, I was going to say, you might want to plan a little Sunday night study party for this one, because these are the kind of problems you're going to want to talk to each other about, as far as getting them set up, drawing pictures, that kind of stuff. All right. I'll be here bright and early Monday morning if you want to come in. Okay.